So at the outset, let us try to understand what you mean by motoring operation. So in order to have motoring operation, the same DC machine is taken. This is your DC machine. Same construction. Field is kept on the stator side and conductors are kept on the rotor side. All right. And the power input in case of motor is electrical. And the power output, P out, is mechanical. Okay, and if this is the operation, then we would say the given DC machine is operating under motoring mode. Motoring mode. So just by interchanging the type of the input, one can make the DC machine to work as a generator, or you can make the DC machine to work as a motor. All right, so that's the what do you say, very basic understanding of motoring operation. You need electrical power in order to get mechanical power output. So for a motor, the efficiency eta can be defined as P out by P in. So what is P out? P out is mechanical. So P mechanical is your power output, and P in, which is nothing but electrical. P out. So this is your motor efficiency. On the other hand, the generator efficiency, let us take it as Ng. So generator efficiency can be found using the same relation, that is output by power input. But in case of generator, you have seen that power output is basically electrical, and power input to the generator is mechanical. So this is the difference. All right. So that's about the preliminary stuff about DC motors. All right. Fine. Next up, we have something known as working principle. So, working principle of DC motor is pretty simple. It works on the principle of electromagnetic induction. Electromagnetic induction. Okay. So that's something like whenever a current carrying conductor placed in a magnetic field experiences a force, and the force acting on the cylindrical surface give rise to a torque, and this torque makes the motor to rotate. All right, so let me repeat. Whenever a current carrying conductor is placed in a magnetic field experiences a force. Force acting on the circumference of cylindrical rotor give rise to torque, and this torque makes the motor to rotate. All right. Now, the force acting on the conductor can be given as F is equal to VIL sine theta. Okay. So this is your motor equation. Motor equation. Okay. On the other hand, in case of generator, you have written E is equal to VLV sine theta. You see the difference. It's one and the same. Conceptually, it is the same, just that you are interchanging the type of input. So E is equal to VLV sine theta is your generator equation. You see, so beautifully you can compare the two machines. All right. Now, This we have already understood. So let's pay our attention to the motor, where F is equal to force acting on the circumference of rotor. Okay, that is nothing but, if let's say this is your rotor, okay, and always rotor is circular, right? So circumference in the sense, say somewhere here, or say suppose here, and this is the radius of the um, rotor. So basically, force into radius will give rise to torque, right? This is what I was talking about. So force experienced by a current carrying conductor on a cylindrical surface give rise to torque, and this torque basically makes the rotor to rotate, and it is normally measured in newtons. And B is equal to flux density in Tesla or Weber per meter square, right? Or Weber per meter square. L is active length of the conductor. Active length of the conductor in meters, SI unit. And theta is the conductor orientation with respect to flux lines. It is similar to the directions what we considered while deriving an expression for E is equal to BLV sin theta, right? The conductor may be oriented in such a way that the movement of the conductor could be parallel with the flux lines, or the movement could be perpendicular to the flux lines, or the movement could be something like inclined at an angle theta with respect to flux lines. Okay, so that's nothing but your inclination angle theta. All right. So this is the equation for force. Okay. So it works on the principle of electromagnetic induction. Okay. Now let us try to understand something known as Fleming's left-hand rules. Left-hand rules. So Fleming's left-hand rule is also called a motor rule. On the other hand, Fleming's right-hand rule is called as generator rule. Generator rule and motor. Now, so today let us make an attempt to apply this Fleming's rule in order to determine the motion of the conductor. Okay, so that's nothing but the left-hand rule. So for that sake, what we can do is, let us consider a two-pole motor, right? Two-pole motor. Let's say this is North Pole, and say this is your South Pole. All right. Let us consider a circular rotor, in which let us consider two pairs of conductors. Okay, one pair and the second pair. Now, in the conductor, okay, now when you say conductor, conductor can be considered as a piece of wire. Conductor can be considered as a piece of wire. So what happens is that, so probably you can visualize this as your conductor. All right. So what happens in DC motor is that on one side the current gets in. All right. So let me keep it in this way. On one side, current gets in, it flows into the conductor, and then it will come out on the other end. So if you consider any conductor, the conductor will have two terminals. at one terminal, the current gets in, and at the other terminal, the current gets out. So on that note, what we can do over here is that on one side, we can show that the current is entering. So entering is shown with cross mark, and the current which is leaving from the other terminal is shown with a dotted mark. Okay, you can see, right? Cross mark and dotted mark. So cross mark is nothing but entering. So that can be visualized with the help of this arrow. Right. So usually, arrow is used to understand the entering and leaving phenomenon. Okay, so what you have to do is you have to imagine a plane of paper. All right, so this is your paper plane. So if an arrow is coming out of the paper, right, out of the paper, let's say the current is coming out of the paper. Okay, so current is being replaced with an arrow. So what you can see the tip of the arrow. So tip of the arrow is a pointy end. So pointy end is nothing but a dot. Okay. So dot basically refers to leave in leave. Current leaves. So at the dotted terminal, we say that current leaves. On the other hand, if the arrow is being shot into the plane of paper, what you can see the tail of the arrow, right? So tail of the arrow can be visualized with an X mark. So X or cross stands for current enter. That's all we have done. On one side it enters and on the other side it leaves, or vice versa. Okay. Similarly, let us say on this side the current is entering, and on the other side, let us say that the current is leaving. Okay. Once you are done with this, you can draw the flux lines. So flux lines are always, originates from North Pole and terminates at the South Pole, right? So from north to south, the flux line goes. That's all. Now let us apply the Fleming's left-hand rule. So to apply Fleming's left-hand rule, stretch the first three fingers of your left hand in such a way that they are mutually perpendicular to each other. The central finger should be pointed in the direction of current. The forefinger should be pointed in the direction of flux. So C for current, center finger. Forefinger, F for flux, the forefinger. And the thumb gives the motion or the force experienced by the conductor. All right, so let's do it. So X is current entering. So let me point the finger in this direction. All right. So my central finger is pointing towards the entering current, and my forefinger is being directed along the flux lines, and my thumb, you can see the thumb is pointing downwards. So at this particular conductor, the direction of force is downwards. So let us mark that force. Force is downwards. Done? Now let us go to the second conductor, okay, in which the current is entering. The same thing. Okay, central finger in the direction of current, forefinger in the direction of flux, and the thumb gives the direction of motion. Once again, over here, the force is acting in the downward direction. Okay. Now let's pay our attention to the current which leaves the conductor. So how do you visualize the leaving phenomenon? The finger should be pointed, towards you, right? So that's what I'm doing. So the central finger is pointed in the direction of leaving current, forefinger along the direction of flux, and the thumb gives the direction of motion. Now you can see that thumb is pointing upwards. So direction of force is upwards. Similarly, over here also, the direction of force is upwards. So basically, what are you seeing? You're seeing something like this. You're seeing something like this. On one side, the force is trying to pull this particular object in the upward direction. And on the other side, the force is trying to pull the object in the downward direction. So basically, the group of forces are helping each other in rotating the rotor. So that's how your motor starts rotating. And this can be nicely visualized by applying Fleming's left hand rule. Right, Fleming's left hand. Something like this. So this side is kind of going up, and this side is kind of getting pulled downward. So basically, you get a twisting momentum, and that twisting momentum basically called as the torque. All right. So this is the application of Fleming's left-hand rule in determining the direction of motion, which in turn gives the direction of rotation. All right. So that's about Fleming's left-hand rule. Next up, we have something known as vacuum. Vacuum. All right. Okay. So next up we have back EMF. Now we're talking about motor, and why are we talking about this EMF, right? So EMF, strictly speaking, we should be talking it in generator. But in case of motor, what happens is that following the motor action, there will be a generating action in the armature. And that generating action gives rise to something known as the back EMF. Okay. So back EMF can be visualized probably with this demonstration. Okay. So back EMF is related to only DC motor. All right. So that's the first thing. Now imagine that you have a stator, all right, in which you have, let's say, two pairs of poles. So your field is stationary, and this is your rotor. It is made up of conductors, right? So this is your armature. Now, in case of DC motor, what happens is that the field system is energized, right? So field system will carry certain amount of flux. And when the current is supplied to the armature or to the rotor. The rotor starts rotating. So the rotor starts rotating, right? Now, this is called as motoring operation. Now, when the rotor is under motion, what happens is that the rotor is going to cut the flux lines set up by the stator, right? So when it is under motion, it is going to cut the flux line produced by the stator. So when the rotor cuts the flux lines produced by the stator, what happens is that there will be an induced EMF in the rotor. So that induced EMF is called as the back EMF. So the back EMF takes place after motoring action. So back EMF takes place after motoring action. That is, once the rotor starts to rotate, it keeps on cutting the magnetic field produced in the stator, due to which an EMF is produced in the rotor conductor. So that EMF is called as the back EMF. Now, the direction of the back EMF can be given by the Lenz law. So as per Lenz law, the induced EMF in the armature opposes the cause. So this back EMF tries to oppose the cause. Okay, so since the EMF is trying to oppose the cause, or it is trying to push the source current, that's the reason it is called as back EMF. It is trying to push back the source current. So that's the reason it is called as back EMF. However, the back EMF, popularly represented as EB, can be given with the same generator formula, phi z np divided by 60A, because the nature in which it gets developed in the armature, it is similar to the generating action. All right, so phi z np divided by 60K. Now, we can write an expression for back EMF with the electrical circuit as well. So, for that sake, let us consider shunt motor. So, basically, what we are trying to do is to develop an electrical equation for back EMF. Okay. So, let's first draw the motor. So, I'm not talking about generator anymore. Motor I'm talking about. Hence, I'm going to write a symbol M. So M stands for motor. So this is your A and this is your AA. All right. This is your armature current, resistance RT. And this is your field winding. And the combination is connected to plus minus external DC. So this is nothing but external DC power input, which is electrical, right? That's all is required for the motoring operation. So this is your external DC power. So the power is flowing from left hand side to right hand side. So this will be my load current, okay, or line current. So this line current is going to get divided into two parts. The field part, ISH, and the armature part, IA, right? So let's say RSH is resistance of the field. Compare this diagram with the generator diagram. In case of generator diagram, you have seen that power was flowing from armature to the load. So this is for generator. On the other hand, from left to right is for motor. So this is electrical, and then the motor starts to rotate. Let's say theta. Theta is the angular displacement. So when you give electrical input, it gives mechanical rotation. So mechanical rotation is visualized with theta. All right. Now we can write KCL expression. So KCL expression is IL is equal to ISH plus. IL is equal to ISH plus. Okay. This is your motor equation. In case of generator, IA is equal to IL plus ISH. You have to observe. So opposite relations we will write for motor and generator. Okay. And you can also apply KVL. Okay. Let's apply KVL in this manner. So the clockwise sense, inside let us apply. So voltage, the same voltage will come across the shunt field winding as well because it is directly connected. So when we apply KVL, what do we have? We have V minus IR. And let us also show the EMF generated VR. This is your back EMF minus plus. So this back EMF normally shown with a small arrow pointing upwards. So this upward arrow simply shows that the back EMF is trying to oppose the source voltage V. Okay. So it is V. Okay, this is V. Let me rewrite. V minus IARA plus to minus C is equal to 0, or V minus EV divided by RA will give you armature current. Will give you armature current. This is one of the very important relation in motor. So armature current IA can be given as V minus EV divided by RA. Next, let us try to understand significance of back EMF. Significance of back EMF. Now, at rest, when the motor is at rest, speed is 0. If there is no rotation in the rotor, there will be no back EMF. So at rest, your armature current IA becomes V divided by RA. Okay. And we can assume some practical values for V and I. So V is the supply voltage, popularly 220 volt DC is used, and RA is the resistance of the armature. You have seen in generators, right? The value for RA generally it varies from 0.1 ohm to 0.5. Let's say 0.5. It's very small because armature is made up of high grade copper. Now, if you consider this typical case, what we will get the value of armature current. So armature current is 220 divided by 0.5. So that's about 110 amperes. No, it's a lot. More than that, right? 440. Because doubling effect you get. Because 0.5 is 440. Very high. In fact, you can call it as dangerously high. So dangerously high current. So what you have seen is that in the absence of back EMF, your motor draws very high current, which is as high as 440 amperes of current. So that means to say, due to this high current, armature may get damaged. So in the absence of back EMF, the motor can draw very high current, and due to this very high current, the armature can get damaged. So this is the very important significance of back EMF. So with back EMF, basically what happens is that you can see the back EMF relation, right? So you can rearrange this equation. So you will get EB is equal to V plus EAR. So with back EMF, so here let me write. With back EMF, what happens to armature current? So let us say this is IA naught, and with back EMF, let us say IA1. So IA1 is V minus EB V minus EB divided by A, which is equal to V is 220 minus EB. EB is V minus IARA. So slightly less than the supply voltage, let's say 210 divided by 0.5. So how much you get? 10 divided by 0.5, that's 20. 10 divided by 0.5, that's. So you can just observe, just with the presence of back EMF, the current can be reduced drastically. Okay. So basically, the back EMF regulates the armature. Without back EMF, more armature current. With back EMF, very low armature current. That's what you can comprehend from this particular explanation. All right. So that's the significance of back EMF. They will ask, define back EMF and explain the significance of back EMF. So whenever it is asked, probably you can take these two examples to explain what happens without back EMF and what happens with back EMF. Finally, and you can write a footnote by stating that, mentioning that back EMF regulates the armature current. Next, let me consider this relation. Okay. Say equation 1. Okay. So I'll write from equation 1. I can write V is equal to, let me take back EMF and resistive drop on the right hand side. V is equal to IARA plus E. So neglecting brush contact drop and armature reaction drop. Next, you write multiply with I. So multiply the above equation with I. So what do you get? V into IA on left hand side. On right hand side, you get EB into IA plus IA into RA. So that is IA square. Okay. So basically, you get a kind of power relation, right? On left hand side, it is voltage into current. Voltage into current is power. On right hand side, you have voltage into current, again power, and you have IA square into RA, which is nothing but I square R loss. Again, it is something like power loss. So IA square into R is called as armature copper loss. Armature copper loss. On the other hand, V into IA. Okay, I can erase this. I don't need this diagram anymore. V into IA. What is it? What is V? V is external voltage, and IA is armature current. So V into IA is called as external power input, right? Power input to the armature, sorry, right? V into IA, because when you say external power input, it should have been V into IL, the line current. But here not considering line current, you are considering armature current. So you can write power input to armature. All right, and then finally we have this term, EV into IA. So this EV into IA is called as power developed in the armature. This is power supplied to the armature, and this is power developed in the armature. So this power developed in the armature is basically mechanical power, right? Because when you give electrical input, motor gives mechanical power output. That's the reason this is also called as equivalent mechanical power development. So you can say that electrical equivalent of mechanical power. Yeah. Okay. Why we are saying electrical equivalent? Because we have electrical relation EV into I. But that refers to the kind of rotations being set up in the rotor. Okay, that's the reason it is called as electrical equivalent of mechanical power development. So that's your power relation. So this is also very, very important. That's all. Next up, we have torque equation. Torque equation. Very simple and very, very important. So to derive a torque equation, let us consider a rotor, circular rotor. Consider a circular rotor. It is under the influence of force. The force is acting tangentially on the surface of the rotor. And let's say the radius of the rotor is r. And let us define certain machine constants. Let F is equal to force in newtons, r is equal to radius in meters, then n is equal to speed in rpm, and phi is equal to flux per pole. Okay, what we defined in generator is the same thing you can define. Phi is flux per pole, Z is number of armature conductors, K is number of parallel paths, and P is number of poles. So we have just defined the machine constants. Then we can write. So, the rotor rotates with the speed of n rpm. So then we can write something like the torque developed in the armature, something like PA is equal to force into distance. Right? Torque is nothing but twisting force. So force into distance basically gives the torque. Over here, that distance is nothing but the radius of the rotor. So F into R is torque. Okay. Then work done by the rotor in one revolution. So work done, you can't say rotor, work done by the motor. Work done by the motor in one revolution of the rotor can be given as W is equal to work done is nothing but force into distance traveled in one revolution. So work done can be given as F into distance traveled, force into distance traveled in one revolution. So in one revolution, what is the distance traveled? So in one revolution, distance traveled is nothing but circumference of the circle, right? Because rotor is circular in nature. So distance traveled is nothing but the circumference of the circle. So you can write W is equal to F into what is the circumference of the circle? It is 2 pi r. 2 pi r. The unit is watt second. Unit is watt second. Then you can write power developed in the armature in one revolution of the rotor is P is equal to, what is the power developed in the armature? Power is nothing but work done divided by time, right? So work done is watt second divided by second gives the unit of power as watt. So rate of electrical work done is nothing but power, right? So W divided by T is power. So W is nothing but F into 2 pi R divided by T. So from where will we get this time? So you know that the rotor rotates at a speed of n rpm. So in 60 seconds, rotor completes n revolutions, right? Or in 1 minute, it completes n revolutions. So time taken to complete one revolution, all you need to find out. So that is 60 by n. So T is equal to 60 by n. Okay. So same thing you can substitute here. It is 60 divided by n, or it is F into 2 pi r into n divided by 60. Or you can rearrange this particular equation something like P is equal to 2 by n by 60. P is equal to 2 by n by 60 into, I will separate out force and radius into F into R. What is F into R? F into R is nothing but the torque there. So you can write power is equal to 2 by n TA, because F into R is TA divided by 6. So let's take this as equation 1. So P refers to the power developed in the armature. Okay, so it is given by 2 pi nt divided by 60. Alright, so let's keep this equation aside. Okay. Now, expression for power can also be written in terms of electrical quantities, right? So you can write in terms of electrical parameters. You can write power P is equal to EB into IA, right? We have already seen in the previous relation. EB into IA is nothing but power developed in the armature. So that is nothing but EB. EB is what? 5ZNP divided by 60A into I. Let's say equation 2. So basically, equation 1 and equation 2 refers to the power developed in the armature. So equation 1 represents power in terms of torque. Equation 2 represents power in terms of electrical constants, right? So one is mechanical equation and the other is the electrical equation. But the two equations represent power. So you can equating 1 and 2. So what do you get? You get 2 pi nTA divided by 60 on one side, and on the other side you have pi z np divided by 68 into IA. So say few things gets cancelled, 60 gets cancelled, n gets cancelled. Yeah, that's all. So here is this equation to get torque developed in the armature, because that is what we are supposed to find out. So torque developed in the armature, EA is equal to 1 over 2 pi into P phi Z IA by Newton meters. So this is the expression for torque developed in the armature. So if you take out the ratio 1 by 2 pi, you can also write EA as 0.159. So 1 by 2 pi boils down to 0.159. P phi Z IA by. So that's the expression for electromagnetic torque developed in the armature. Very important. So if an expression for torque is asked, you are supposed to solve till here. Okay? Till this extent you have to derive. I take 5 more minutes. This will help you in solving the problems. So just write unknown. So we have derived an expression for torque developed in the armature, TA. So we found TA as 1 over 2 pi into P phi Z into IA by A. So this is the expression for torque. Now it's called as torque developed in the armature. So this is equivalent to, you can visualize something like the torque which is developed within your IC engine, right? Within your IC engine, the bike engine what you have. If the torque is measured at the crankshaft of the engine, that can be compared with the torque developed in the armature. But the actual torque which is available at the motor shaft, which will be slightly less than the developed torque, because there will be losses associated. The losses as in frictional loss, windage loss, etc., etc. Windage loss is nothing but the surrounding wind provides some kind of resistance to the flow of motion, to the motion. So that is called as windage loss. So the actual torque, available at the motor shaft is called as shaft torque, and it is denoted by TSH. So basically, your armature torque is equal to shaft torque plus loss torque. So this loss torque is due to the two components: friction and windage. So the actual torque which is available at the motor shaft, which is called as shaft torque, is nothing but armature torque minus the loss torque or the loss torque. So what you get at the armature is more than what you actually getting at the shaft, because at the shaft there will be some friction, etc., etc. Right, in your IC engine. So this is the torque developed in your IC engine. So when that torque flows to the wheels, the torque has to bear some kind of losses, some kind of friction in the gearboxes, some kind of friction in the wheel, etc., etc. So the actual torque which is available at the wheel is less than the one which is developed in the IC engine. Okay, so that is the for problems you may need this. Okay, so normally PSH can be found using the formula 2 by n divided by 60 into, sorry, yeah, it is other way around. It is power output in BHP. Okay, power output in BHP divided by the speed divided by speed. So this is how you can find out. So 1 BHP is 746 watts. You can check. This is how you calculate the shaft torque in case of a practical machine.